So in this video, we'll have a look at applicatives and how do they differ from a functor, and in particular, what applicative can do more than a functor, since as we know, and as we can tell also from the applicative type class declaration, each applicative has to be a functor, therefore a container that can use functions on the values it contains. But on top of that, an applicative has to implement some other functions that we can see here. And the main goal of implementing this function is to have a container as a computational context. And well, now I know that computational context is kind of a very abstract term, but hopefully after this video and after some examples, you should have an idea of what is meant by a computational context. So at the bottom of the type class declaration, we see this line, which is telling us that the minimal functions that we need to implement in order to have an applicative are the pure function, and we have to define either this operator or a lift to a function, and then the rest is derived from these definitions. Therefore, let's start by having a look at pure, and we see that pure is a function that, given anything, returns that same anything inside an f, where the f is meant to be an applicative. And in order to test what this pure is doing, well, we'll need some applicative instance, of course, and by asking once again for the infos of applicatives, right after the type class definition, we see some known instances that are already present in Haskell, and in particular, we see that lists and maybes can be used as applicatives. So let's test this pure with any value, since we know it can take anything, and specifying the return type, since from the moment that can return also anything as long as wrapped inside an applicative, we should specify what that anything should be. So in this case, let's try to get back a maybe int, and we see that pure returns the argument it got in the context of a maybe. Therefore, it is just constructing a maybe with that argument. And the only constructor of a maybe, as we know, that can take a value is the just. Therefore, it makes sense that given a value, we get back a just of that value. But we can, of course, also test this same expression to be evaluated in a list of integers, since, as we saw, also list can be considered as applicative, therefore can use the pure function, and we see that this returns a list with a single element. So what this pure is doing is just taking a value and using that value to construct an instance of whatever applicative we are working in. So it's kind of a generalized constructor, but the correct way to look at it is not as a constructor, rather is something that is able to take anything that is present at the plain Haskell level and lift it into the computational context that we are working with. Because remember that applicatives are meant to be computational context. And in particular, this function is called pure because the only idea of having containers that represents computational context is all we need in order to have side effects in a purely functional programming language, which is Haskell, since it is kind of wrapping the computation we are performing into a sandbox. Of course, the actual implementation has a lot of details more than just this high level explanation. But since there is this possibility of handling side effects with containers that can be seen as computational context, the action of lifting a raw Haskell value inside that computational context should not have side effects, and that's why this function is called pure. Now, in order to understand how it is possible that applicatives can be seen as computational contexts, therefore a context on which we can perform computations, we should understand what this operator is doing. And well, the name of this operator is AP and stands for apply. And we see here that it takes two arguments, of which the first is a function which is already in our context, as we can see from this f that goes from an a to a b. Then it takes an a which is also in the same context and returns a b in that context. And well, since the name of this operator is apply, it should not be that hard to imagine that what this operator is doing is taking this function and an input and returning the output of that function with that input. But the peculiarity of this operator is that everything is done inside an applicative, therefore inside the container. And in order to understand what this means, let's try this in GACI and say we are working with maybes. So in order to use the apply operator, we'll need a function that is wrapped inside a maybe. So I'm using the just constructor. Then of course use the operator and giving as second argument the expected input of this function wrapped in the same context, which in this case is the maybe context. Therefore I'm writing here just, and well, this function expects a number. Therefore I'm giving here a number, and we should expect back whatever returned this function, therefore a number, wrapped inside that same context. And this is in fact what happens. And notice how in this expression we only work with maybes. And once we ask to evaluate this expression, we are basically taking this function and this input and requesting to evaluate those inside a new just like so. And we see that this works properly, with the only difference being that we don't need to deconstruct the arguments for reusing them in order to construct a new instance, but this is done automatically thanks to the apply operator. And if you look closely, you'll notice that if we remove this f, this type signature is identical to the one of the f map, since, well, we know that this f here, even if it's marked as an applicative, has to be also a functor. So the only thing that changes between this type signature and this type signature is the f that we find right here. And in fact, we could write this same expression like so to use the partial function application. In fact, say we want to use only the plus function, and well, we know that the plus operator requires two arguments, but if we provide only one argument, then we get back a function. Therefore, this can be a clever way to construct a function that is wrapped inside the container. And here we got a valid function inside maybe context. And well, now we can just use this function that we get from this expression with an apply operator and providing the remaining argument. And this expression works just fine. Well, this should not be anything surprising, since of course this is a valid input for the apply operator. This also. Therefore, it should not be that magical, the fact that we get back the expected result. So now that we have an idea of what the minimal functions are doing, let's see what the computational context of maybes and lists are meant to be in order to do some practice with the basics of applicatives. And well, the computational context of the maybe applicative is to express a computation that at some point may fail. And in order to show you this, well, recall that we can have a read maybe function by importing the text.read module. And now we have available a read maybe function, which given a string tries to get back a maybe of a specified type. And we can use this red maybe in order to get some values from a string, as we know, and we'll use it in order to try to get numbers from two strings that are given. And in order to do that, I have defined here a function that takes two strings, and those two strings should contain numbers. And if everything goes right, this function just uses the plus operator fmap on the first argument, which using red maybe should return maybe int. Therefore, this expression evaluates to a function that goes from an integer to a number, and then applying this function, which is inside a maybe context, to the result of the second red maybe, and this whole expression returns a maybe integer. So this is a valid function, and we can now test this add strings with two strings as an argument, and we see that this gets evaluated correctly since we are providing actual numbers inside a string. But if we here provide a string which is not a number inside, well, of course, this red maybe will evaluate to a nothing since it cannot find a way to transform this string. Therefore, it returns nothing. And well, since by using an applicative, we are expressing here a computation that may fail, we will get back a nothing. So by using the maybe as an applicative, we have successfully brought a computation that may fail in just one line of code. So it should be clear how maybes can represent computation that might fail, but now let's see what is the computation associated with the lists, since of course lists are good at being lists. How it is possible that lists can represent computations? Well, they represent the most common computation that you can do with lists, which is to iter through the list. And perhaps this can be more clear by looking at some example. And we'll write our addChoose function that we use with lists in an applicative way. And in order to do that, well, of course, we'll need the plus operator, and we'll need to provide to that operator the first value, but this value is just a plain Haskell value, and it is not an applicative, and neither it is inside a container, so we could not even use fmap, but we do have the pure function that can take this value inside whatever computational context. And well, as written here, this expression evaluates to a +2 function that can be used with any applicative, and it is equivalent to write directly the +2 function provided as an argument to the pure applicative function. But remember that pure to evaluated as a list of, well, in this case, integer, just wraps that value inside a list. So what we are writing here in order to make this expression just work with list of numbers is just writing the result of this expression to be evaluated as a list, therefore to wrap the number inside the list, which in this case is also the computational context. And we see that what we get back with this expression is a list of functions. So what we wrote is something like this. Well, this is just a way to write a function inside the computational context of lists. And back to our original expression. Well, for now we want only to work with lists. This is the expression we would write in order to write our famous addChoose function, and we'll see that this version of addChoose works just fine. But actually, lists seen as applicatives are able to do much more, and in particular, well, I have substituted the pure two with a list containing a 0 and a 10 in order to show you what is going on behind the scenes. And we see that with this expression, we get back a list of length 6, which happens to be 3 multiplied by 2. So what is going on? Well, to make this more clear, we can use the tuple constructor, which is also a binary function that returns a tuple with the argument. So we could use this same expression with the tuple constructor in order to see what we are using for each element of the resulting list. And we see that, well, the first three elements are just 0 plus 1, 0 plus 2, 0 plus 3, and the second three elements are 10 plus 1, 10 plus 2, and 10 plus 3. So with these examples, it should be clear what is the computational context of a list too. So with this, we should have an idea of what applicatives are meant to be. And the main takeaway is that applicatives are functors, which, as we know, are containers that can use functions, but these containers are considered as computational context, and that means that they are abstracting computation that, of course, may vary depending on the container. So we'll use what we learned in this video also in the next one, when we will introduce monads and we'll see the functionality that the monad type class implements on top of the one we saw until now. So if you learned something from this video, consider to subscribe to the channel. Remember that in the description below, you'll find a link that allows you to delegate your ADA to Harmonic pool in the case you wanted to support the creation of this content. In any case, I want to thank you for your time. Remember to stay decentralized, and I will see you in another video. Bye bye.